Good day to you all. My name is Arnold, and I'm going to be joining you this afternoon for our Yebo Physics tutorial, where we intend to solve questions 30 to 35. So those are the questions that we intend to look at. And right now on our screen, I'm showing question 30, and that will be the first question that we're going to try out together. Please let me know if I'm audible for those that are joining on Teams meeting. Please do confirm if I'm audible. You can just type in the chat box, or you can unmute and let me know that I'm audible. Okay, I can see some thumbs up there confirming that I'm audible, and I also believe that the screen is visible. So without wasting much of your time, we want to go through questions 30 and up to 35, and these questions are applications of Gauss law. So those are the questions that we want to tackle this afternoon. So if you have any question as we're solving the problems through, don't hesitate to type in the chat box and seek for clarity on any of the questions that we will be solving. I will be able to see your comment on the chat box. In case if you want to unmute, feel free and unmute will give you the chance to give your contribution. So the first question that we have, it's number 30, which states that the electric field in the region of space shown is given by E is equals to 8 in the I direction plus 2y in the J direction. That's Newton per Coulomb, where y is in meters. What is the magnitude of the electric flux through the top surface of the cube shown? So the question is interested in us finding the electric field on the top surface of the cube. So this is the top surface of the cube. So we are interested in finding the flux through the top face of the cube. That is what the question is asking for. And you should recall from your learning that when, okay, maybe let me write down the data that were given. E is equals to 8 in the I plus 2y in the J. That's our electric field, Newton per Coulomb. And we are looking for electric flux, remember. So we know that our electric flux is equals to the integral of EDA. You should be familiar with this at this stage, right? Now, the electric field strength we are given, but this electric field strength has got two components. It has a component in the I direction and a component in the J direction. But we are considering the top surface. So if we're considering the top surface, which means the contribution of the electric field that is perpendicular to the top surface is that of the y direction. The I direction will be parallel to the top surface, hence it's not considered, right? So if we are to solve this or choose this, becomes phi E equals to E EDA, right? And what is our electric field strength? Our electric field strength is 2y. Okay, our electric field strength is 2y because we're considering the J direction only. I hope that is clear. We're considering the J direction only. We will not consider the I direction. Why? Because it is parallel to the top surface of the cube. So continuing, in place of E, we will put our 2. And the integral of our area is as a result of dx and dz, right? and dz, because y is not contributing in calculating the area of that top surface, right? So it's going to be dx dz. That is our area, okay? Because we are multiplying the electric field strength and the integral of the area. So integral of dx will give us x. So this phi becomes 2. Integral of dx will give us x. The integral of dz will give us z. Now, since this is a cube, so this will be 2. For x, it's 3 meters. Our z is 3 meters again. So that becomes 2 times 3, that's 6. Am I right? Oh, okay. I missed something. Just to take you back from this. Otherwise, everything is okay. Our electric field strength is 2y, by the way. Our electric field strength is 2y. But our y, as you can see from the diagram in the question, it's 2 meters. So that becomes 2. Our y, no, it's not. It's 3 actually. Our y, 3. Then we said our dx, x, and that will be x, that will be y, and that will be z. So that will be 6, and our x is 3, and our z is 3 again. So that becomes, flux becomes 6 times 3, that's 9. 6 times 3, that's 18. 18 by 3 should be 54. All right, so do we have any 54 there? Yes. Oh, this is flux, by the way. I'm giving the incorrect units. This is flux, so that's Newton meter squared per coulomb. So that's basically how we go about this particular question. So we can check and see if we're in the right direction. So that is indeed the question that we expected to get there. So let me know if there are any questions. I see there's a question on the chat. Right, so someone is asking the first question, what are we doing? So I'm not sure if you answered because we've gone through the question. We've just gone through the question. So the question was asking for electric flux. So I'll just display the question again for the sake of the question. So this is the question, right? It says we're given an electric field, and this electric field that we're given is a contribution in the I direction and a contribution in the J direction. All right? I direction is along the x-axis, J direction is along the y-axis, right? And we're being asked to find the magnitude of the electric flux through the top face of the cube. So I've shaded the top face of the cube, right? Now we know that flux, when calculating flux phi is equals to the integral of E dot dA. So which is the same as phi being equals to E integral of dA. Right. Our electric field that we're given is 8I plus 2y in the j integral dA. But now, remember what I said. We said the I direction is the electric field that is parallel to the x-axis. Hence, it is not perpendicular to the top surface. So it is in this direction. Okay? And remember, when we're calculating flux, we're looking at the area that is perpendicular to the electric field. So the electric field in the I direction is not perpendicular to the top surface. Hence, it's not contributing, right? So which means it's out. So we remain with our electric field contributing to the flux as 2y integral of dA, right? Then our 2y, our y is 3, the length of the side y of the cube is 3. Then we remain with integral of dA. We now look at the area of the top surface. The area of the top surface is as a result of dx and dz. The z direction and the x direction to calculate the area. Okay? So that will be 6 integral of dx and dz. 6. If you integrate dx, you'll get x. If you integrate dz, you'll get z. And if you check the dimensions of that cube, it's 3 by 3. So it's equals to 6 by 3 by 3. Hence you get your 54. So I was responding to the question that was sent by Simlindile. Just to go through again that question and hope that it makes sense. Okay, he's confirming that he is following. All right, thank you for that. So I don't see any other questions or comments on the chat. So I guess this suggests that we are all fine with question 30. Now let's move on to question 31. Okay. Question 31 reads, charge of uniform density 0.3 nanocoulomb per square meter is distributed over the xy plane and charge of uniform density negative 0.4 nanocoulomb per square meter is distributed over the yz plane. What is the magnitude of the resulting electric field at any point not in either of the two charged planes, right? So we need to put a sketch first. We need to put a sketch. Like that. So make this to be our y, this to be our z, x, and this to be our z. Now, what does the question say? So, first and foremost, the sketch helps us to visualize the question. We've got a uniform density of 0.3 nanocoulomb per square meter distributed over the xy plane. So this is our xy plane. So we can choose to represent it like this. This is our xy plane, right? and this is 0.3 nano coulomb per square meter. Then we are also told that we've got a negative 0.4 nanocoulomb distributed over the YZ plane. YZ plane. So the YZ plane is this side. It's on the other side now. Okay. So it's something like this. And you know, this is the y is perpendicular to the x, perpendicular to the z. So these three planes are perpendicular to each other. Right, and we are told that we have negative 0.4 nanocoulomb per square meter. Now, what do we do here? We have to use our knowledge on Gauss law. What do we say now? We know that here, when considering a single plane, if we're going to consider a single plane, if we were to consider a single plane like this one, right? And we put our Gaussian surface, which protrudes on both surfaces, right? It's protruding on the back side and the front side, okay? So if we were to do that, then we would know that our phi enclosed is equals to 2 EA, because this Gaussian surface is covering both the front side of the plane and the back side of the plane, right? And we know that this is equals to charge enclosed over epsilon naught, right? But there is something that you probably already know, that the charge enclosed is equals to sigma A. So I'll just circle this because this is important, okay? It's equals to sigma A, and sigma being our charge density, right? So if you reduce this expression, 2EA become equals to sigma A over epsilon naught, right? And to find the electric field, it's going to be equals to sigma A. Okay, rather the A is cancelled out, right? The A is cancelled out. This goes. So this becomes sigma over 2 epsilon naught. Okay. So this is how we can then calculate the electric field resulting at each of the planes. This you already know. This is the electric field at each of the planes. So we're going to say this first plane, which is the YX or the XY plane, we'll name it E1, and this one we'll name it E2, right? So E1 is generating an electric field, E2 is generating an electric field, and we're supposed to calculate the contribution of these two electric fields at a certain point. So if you are going to consider these fields, they are perpendicular to each other, right? We've got one emanating from this side and the other one emanating from this side, right? So which means somewhere in the space there, that's where we have the contribution of the two electric fields. And already we can see that this is a 3D Cartesian plane and the electric fields are perpendicular to each other. Right? So to find the resultant electric field, will be equals to the square root of E1 squared plus E2 squared. So that is how we should find the resultant electric field that we are being asked to find. So this is the formula to calculate for your E1. That's the very same formula again to calculate for your E2. So now let's solve E1 and E2. And then we find the contribution of the resultant of the two electric fields. Could there be any questions at this point? Because once we have understood the concept on which we should solve this problem, then the rest is now punching in values and substituting. All right, so there's a question, why are we using 2EA? Okay, so I'll try and explain again. Phi is equals to EA. We agree, right? Phi is equals to EA, right? Phi is equals to EA. But now we have a plane. We have a plane, right? A rectangular plane, right? And in this rectangular plane, we're going to put a cylindrical Gaussian surface, right? And this cylindrical Gaussian surface is entering inside the plane, so which means we have a contribution from this side and a contribution from the other side. So hence the flux becomes twice as opposed to considering one side, because we have a contribution of the flux on both sides of the plane. I'm not sure if this answers your question, Avile. Okay, if you understand, then we can proceed. So now we can solve for E1. Like I said, it's now a matter of substitution. E1 sigma is 0.3 times 10 to the negative 9 all over 2 epsilon naught, which is 8.85 times 10 to the negative 12. So we punch that. Now we punch that. It's 10 to the negative 9 all over 2 times 8.85. What is happening to my... So you can punch with me to confirm our answer. See if we get the same answer. Time, okay. So this becomes 2 times 8.85 times 10 to the power of negative 12. So we get 16.949 Newton per Coulomb. Then for E2, it's going to be equals to negative 0.4 times 10 to the negative 9 all over 2, 8.85 times 10 to the negative 12. So let's punch and see what we get. So we just change this to 0.4. We get 22.6 Newton per Coulomb. Now, once we've done this, then to find our resultant, we then use that equation. Then we can say the square root of our ans squared plus 16.949 squared. So our E resultant is going to be equals to, say it's 16.95 squared plus negative 22.6 all squared. And from there, we'll get a resultant of 28.2 Newton per Coulomb. So like I said, this is now substitution. As long as you have understood how we go about the question, like I explained, then so this is indeed how we're supposed to solve the questions. Could there be any questions or comment on this one? Yes, indeed. For I see Avila was following on the punching. Yes, indeed, we get 16.49. That was for E1. Then for E2, 28.2. Then to find the contribution of both of those, then that becomes the square root of the individual contributions. All right, so let's move on to question 32. Right, question 32, what does it say? Question 32 reads, a long non-conducting cylinder of radius 12 centimeters has a charge of uniform density 5 nanocoulomb per cubic meter distributed through its column. Determine the magnitude of the electric field 5 centimeters from the axis of the cylinder. So it's 5 centimeters from the axis of the cylinder. So again, we'll start by putting a sketch. So we've got a cylinder with this 12 centimeters, right? 12 centimeters radius. Okay. Right, so this is our cylinder. And this is 12 centimeters. Okay, and what next are we given? Or are we told we are supposed to calculate the magnitude of the electric field 5 centimeters from the axis of the cylinder. So where is our axis? So this is the axis of our cylinder. That is the axis of our cylinder. So now we have to find a perfect Gaussian surface, which is going to be a cylinder, right? And we're calculating at 5 centimeters. So if we're going to do this, so this is our Gaussian surface at 5 centimeters from the axis. Okay, and it's positive, right? So we've got a positive charge, so it's a positive charge. Zero comma 5, yeah, it's 5.0 nanocoulomb. Okay, uniform charge density is equals to 5.0 nanocoulomb per cubic meter, right? And again, we should know that the charge enclosed is also equals to sigma V, because we're considering charge per volume, right? So now that we have put our perfect Gaussian surface at 5 centimeters, we now apply our Gauss law, right? Say the integral of E dot ds is equal to the charge enclosed over epsilon naught, right? And this is E integral of ds, which is equals to charge enclosed, it's rho v, so it becomes rho v over epsilon naught. So if we are to find the surface area of our Gaussian surface, this is a cylinder, right? So you are interested in finding, okay, so this is L, the length of our Gaussian surface. So to find or to calculate the surface area of our Gaussian surface, it will be to multiply the circumference and the length to find area. If you cut a cylinder, so for example, this is our cylinder. If you cut this cylinder, what do you remain with? You remain with a rectangle, right? Which is our width and this is our length. So basically what we are saying, if you cut this cylinder, this top part forms or was forming the circumference. So it is the circumference times the length to calculate the surface area of our Gaussian surface. So this becomes E dot our surface area, which is the circumference, which is 2 pi r, which is the radius, times the length L, okay, equals to our charge density, which is rho, and what is our volume? Remember that volume is equals to area times the length, okay? And what is our area? It's pi r squared. So volume is equals to pi r squared L. Okay, so you're just applying your mathematical knowledge, right? So your volume is going to be equals to pi r squared L over epsilon naught. All right. Now you cancel like terms. So here we are considering for r of our Gaussian surface less than the radius of the cylinder. So now what do we do? I think we can cancel out the common, cancel out that, cancel out this, cancel out that, cancel out that, cancel out that. And what do we remain with? E is equals to sigma over 2 epsilon naught. Forgetting the radius, so like that. All right, so once we've done this and once you've understood this, that you have solved the problem, what remains is the substitution. So our E is equals to our sigma, it's 5 times 10 to the negative 9. So we've been asked to calculate it. That is 5 centimeters, which is 0.05 over 2 epsilon naught, that's 8.85 times 10 to the negative 12. And what you remain with is punching. Let's go back to our calculator and punch that. Oh, I see some have already calculated the answer. Avril is getting 14.2. Anyone else getting 14.2? 14.12? Negative 12. Right, I'm also getting 14.12. Anyone getting a different answer? Let's check if that is correct. So indeed that is 14.12. That is how we're supposed to do the computation. Right, that is how we're supposed to do the question. All right, so there's a question there. There's a question there. It says, in the analogy that we have used, isn't the Gaussian surface supposed to be bigger than the charged cylinder? Anyone wants to comment on that question? Anyone who would want to respond to the question? There's a question on the chat there. Anyone who wants to respond to the question? Anyone who would want to respond to the question? So the other question that you are asking is, how did we arrive at the specific Gaussian surface? So the specific Gaussian surface, remember I told that we have got a long non-conducting, cylinder. So a Gaussian surface should be perfectly matching that cylinder, right? The Gaussian surface must be perfectly matching with the shape of the object that you are given, or the charged object that you are given. So if you are given a cylinder, then a perfect Gaussian surface should also be a cylinder. I answered with that one. If you're given a cylinder, then also your perfect Gaussian surface should be a cylinder. So anyone who wants to respond to the question that was raised there, you can unmute your mic or you can type in the chat box. All right, I don't see any any comments in the chat. So why we have chosen our Gaussian surface to be less than 12 centimeters, it is because we have been asked to calculate the magnitude of the electric field at 5 centimeters. So we are enclosing everything that is at 5 centimeters. Hence, um, our Gaussian surface is covering 5 centimeters so that we include the charge distribution that is within a radius of 5 centimeters. Waiting for Tsepo to respond, but otherwise, we move on to question 33. Right, so question 33, what is question 33 saying? It says a long non-conducting cylinder of radius 12 centimeters has a charge of uniform density 5 nanocoulomb distributed throughout its volume. Determine the magnitude of the electric field at 15 centimeters from the axis of the cylinder. So you see for this one, now our Gaussian surface should be at a radius of 15 centimeters because we want to include everything that is 15 centimeters from the axis. So if we are to sketch this again, and this is our axis. Of centimeters. Now our Gaussian surface should be at a radius of 15 centimeters. Okay, and again the charge is positive. There's a positive charge. And the radius from the axis now it's 15 centimeters. Okay, so now our Gaussian surface is covering the 12 centimeter radius cylinder. So we go back to the same analysis. Integral E dot ds equals to our charge enclosed over epsilon naught, and we have got our E dot, or rather, we can take this out. E thing equals E dot ds, and our Q, we now know that it's charge density rho V over epsilon naught, and we know that our V is equals to pi r squared L. So we're still considering our L to be the same length L. And what do we know from that? Our surface area E dot 2 pi r, which is our 15 centimeters Gaussian surface, right? R, which is equals to rho pi r squared L over epsilon naught. Okay, so our r is equals to 15 centimeters, our small r is equals to 12 centimeters. So now we cancel out, this goes, that goes, that goes. So we are looking for E, that becomes rho r squared over 2 epsilon naught r squared, r just r dot squared. So this is the case when r is greater than the radius. So now what remains is for us to find the magnitude. That's 5 times 10 to the negative 9 times r, we say it's 0.12 squared over 2, 8.85 times 10 to the negative 12, 0.15. Okay. Not sure if, Tsepo, you noticed the difference between the two situations. The first one, the radius was the radius of the Gaussian surface had to be smaller than the radius of the cylinder. In this case, the radius of the Gaussian surface is larger than the radius of the cylinder. I'm not sure if you are picking up the difference. 1, 2 squared, and this becomes 0.15. So I'm getting 27.11. I'm not sure if that is what you are getting. All right, so it's confirmed that it's clear. It's clear. Let if it's making sense. So basically, that is how we go about those two cases. So you should pay attention when giving such questions. So the choice of the Gaussian surface has to enclose the charge that you, the charge at which you are supposed to calculate the electric field or the magnitude of the electric field. So that's what determines your Gaussian surface, whether it's going to be inside the cylinder or outside the cylinder. So those are the things that you have to consider. Shall we proceed to question 34? If we are happy with these two questions, and that looks similar but entirely different. So they look similar but they are not the same. We work them out. differently. They look similar, but they are not the same. So you'll take note that on question 32, was it 33? Okay. On question 32, we're calculating at 5 centimeters from the axis, right? Which is the radius, which is happening to be less than the radius of the cylinder. But on question 33, we are calculating for an electric field which is at a radius greater than the radius of the cylinder. Hence, our Gaussian surface has to be larger than the radius of the cylinder. Now let's get to this one. Worth 10 marks. Worth 10 marks. Did you notice that? Question 34 is worth 10 marks. And question 33 was just 2 marks. Question 10 marks, meaning this is a question that you may find in an exam because it really requires a lot of working. So let's get on to it. Let's get on to it. So this is question 34. A long non-conducting cylinder has a radius of 6 millimeters and has a non-uniform volume charge density, right? Given by sigma alpha r squared, where sigma is 6.2 millicoulomb, and r is the distance from the axis of the cylinder. What is the magnitude of the electric field at a point 2 millimeters from the axis? You've been given a hint there that the charge enclosed is an integral of rho dv with integral limits of 0 up to 1. So how do we go about this question? So this question is different from the 2 previous questions in the sense that the charge density is not uniform, right? The charge density is not uniform, and here the charge density was uniform. Here it's a non-uniform. Okay, so it's varying. So let's get onto it. Let's get onto it and see how we break it down. So I'll put a sketch like that, and this is a sketch of my cylinder, right? I've just chosen to put it in like a 3D representation, sort of like, because there's a reason why. So let's look at the data that we are given now. So first and foremost, we know that Q is equals to rho dV, right? Q is equals to rho dV, which means delta Q will be equals to alpha r squared dV. Why? Because we are told that rho is equals to, from the question, alpha r squared. Okay, that's the first thing that we're given. Then we can then check what is this dV. dV, it's volume, right? Remember, we said V is equals to pi. Okay, for now it will not work as pi r squared. So volume, we said it's a L, right? But in this case, we need to consider this thickness, which you are going to call our dr. Okay, so we're going to call that dr. Why? So that we can use this volume to be equals to 2 pi r L times dr to get volume. So I'll explain why we're doing that. I'll explain why we're doing that. So if we cut, now this is the explanation why we're finding the volume like that. If we cut at this point, remember this is a cylinder, and when you open a cylinder, a cylindrical surface, it becomes a rectangle, right? If you cut open it, it becomes like this. Okay, if you cut open it, this is how it becomes, right? And where is our L? This side is our L, and where is our 2 pi r? Our 2 pi r is the circumference, so it's this side which was forming the circumference. So it's 2 pi r. So now I have 2 pi r L. But remember, when calculating volume, it's length times width times height. So this is our thickness, okay, which is our thickness, which is the same as at this point, the thickness, which I highlighted here, which is dr, which is a small r. Are we happy with that so far? Because we need to understand that point so that we can move forward. Do we understand that part? So what have we done there? We've just taken this cylinder and we've sliced it and we've opened it like this. So if you've sliced it and open it like that, it becomes something like this, right? And to calculate the volume of this book, it will be 2 pi rl, which is this top surface, which was contributing to the circumference. Okay, then this is the length, right? Then the thickness, find the thickness, which is this part, right? Remember, volume is length times width times height. Okay, so this is our width, which is the circumference, 2 pi r. This is our length and the thickness. Are we happy with that so far? So this is explaining why we are having our volume like this. So that now our dV is equals to 2 pi, okay, I'll just 2 pi rl, 2 pi rl dr. So I've just taken it from there. Okay. Now we go back to our equation, which is our dq. Okay. dq is equals to alpha r squared times dv. We now put our dv, which is 2 pi r l dr. Okay? But our equation from Gauss law is equals to charge enclosed over epsilon naught. And we have been given a hint there that the charge enclosed is equals to that integral. So which means if we put an integral there, like if we put an integral there, if we put an integral there, integral on both sides, we'll remain now with q, which is our q enclosed given in the equation. So our integral should run from 0 to 2 millimeters. Okay, so I'll just say from r is equals to 0, r is equals to 0 millimeters, and r1 equals to 2 millimeters. So I'll just give my upper limit is r1. Okay, so I'll put my alpha r squared 2 pi r l dr like that. So the next thing, I'm removing constants and remaining with r inside. So you remain with alpha 2 pi l integral of 0 to r1, and here we've got r cubed dr. Okay, once we've done that, integrate 2 pi l, that becomes r to the 4 over 3, right? Yeah, if you integrate that, r to the 4 over 4, 3 plus 1, yeah, 4, with limits of 0 to r1. If you substitute the limits there, it's going to be alpha 2 pi l r1 to the 4 over 4. If you put 0, obviously the lower limit will give you 0. So this is our charge enclosed. Now that we have our charge enclosed, what do we then do? We now go back to what we already know, that E A is equals to charge enclosed over epsilon naught. And our area enclosed is the area enclosed by a point 2 millimeters from the axis. So therefore, you should remember now, if you were to put a Gaussian surface there, our Gaussian surface should be having a radius of 2 millimeters. Okay? And we've said 2 millimeters. We've said 2 millimeters is represented by R1. So we'll maintain that. So our area becomes 2 pi R1 L equals to our charge enclosed, which is sigma 2 pi L R1 to the 4 over 4 over epsilon naught. Okay. If we simplify that, you're taking everything down now. E will now be equals to alpha 2 pi L r to the 1/4 over 4 epsilon naught divided by these guys there, right? Which will be the same as multiplied, right? So the same as multiplied by 1 over 2 pi r1L. So this is just a mathematical analysis. R1, 2 pi there. Yes, did I do that correctly? Yes, I think I did. Cancel everything. R1 cancels that. We remain with 3. So you remain with your E being equals to alpha r to the 3 over 4 epsilon naught. Are you still there? Guys, are you still there? Show by thumbs if you are following. If not, please let's ask questions in the chat. So that is what we remain with. I think I've simplified that. Correct me if there could be a mistake, but I think I've done that. Okay. Comments in the chat. Even if you are following, please comment to say you are following so that I know that people are still there with me. So E is now equals to alpha r to the 3 over 4 epsilon naught. Alpha is 6.2 times 10 to the negative 3, 2 times 10 to the negative 3 cubed over 4, 8.85 times 10 to the negative 12. I'm not seeing any comments. What is happening? What is happening? What is happening? I said if you are still in the meeting, show by a thumb or by a comment that you are still there and you are following. If you are not following, also show by chat, send a message and let me know at which stage I stuck. If you are happy and you're following, again, just comment and let me know that you are following what we are doing. So I'll continue with the punching, also punch with me. Suspend 2 times 10 to the negative 3. Okay, someone has already passed the answer there. Let's see, what do I get? Times. Right, so I'm also getting 1.4. I think there's someone who put their answer as 1.4 as well. Yes. Someone also put their answer as 1.4, which is, yeah. Okay, all right. Someone's, all right. All right, we'll do that right away. So a quick rundown of how we have tackled this question. So remember, the question says we've got a long non-conducting cylinder of radius 6 millimeters, right? And has a non-uniform volume of that. So the catch is on the fact that the charge uh, uh, is non-uniform. Okay, the charge density is non-uniform, right? That's where the catch is. And I put an illustration. Okay, you are given a hint, right? To say Q is equals to that 2 rho TV. Okay. Then we know that EA is equals to charge enclosed over epsilon naught. This you already know, right? And this is E is equals to 2 pi R1. We said R1 is equals to 2 millimeters. I'm not going to solve the entire question times L, the length, which is equals to Q enclosed over epsilon naught. So basically, this is how we solve the question. The next thing would be for you to put the value for the charge enclosed if you have it. But now, in this question, we are not given the value for the charge enclosed, but we have been given an expression Q is equals to integral of dV, all right? So what then do we do next? We then look at the information that we are given and the information that we know to say, okay, a small q charge of dq is going to be equals to rho dv. This is something that you already know from q being equals to rho v. But now we're considering a small charge so that we can sum it up, okay? A small charge. But then we realize that this dv, which we have there, we don't have it, we're not given. So we are now supposed to use our knowledge to say, okay, by the way, volume is equals to the area times the length, right? And in this case, now, this is where I was putting an illustration of this cylinder, which has got a thickness of dr. And I was saying, if you cut this cylinder at that point, you will then have a shape like this. You will then have a shape like this. Okay, that's poorly drawn, but visualize it in 3D. You will then have a shape like this. And this is your thickness. This is your thickness, which is dr. Okay? And from this front part to there, this is the circumference. That's the circumference, right? Because you have cut open this shape. This becomes the circumference, and we know that circumference is 2 pi RL. Okay, the circumference is equal to 2 pi R. 2 pi R actually. 2 pi R. Where am I putting? 2 pi R. The circumference is 2 pi R, right? And this edge going down is your length, right? So the volume is now equals to the area, which is 2 pi R L times dl. So your volume becomes 2 pi R L dot dr. Why? You have to find the volume, length times width times height. Length times width times height. So that is how we've found the volume. Okay, why do we find this volume? So that we can have dv, which we don't have. Dv is equals to 2 pi r l dr. This is our dv. This is our dv, which we are then going to put in this equation. All right, so our dq is equals to rho. Then in place of dv, we put 2 pi r l dr. Okay, then this sigma we've been given that is equals to alpha r squared. So our dq is equals to alpha r squared. Then we continue 2 pi r l dr. So this is small q. We now want to find our q. And to get rid of this dq, we integrate dq. If you integrate dq, you get q, right? So if you integrate both sides, so if you integrate dq, you'll get q, which is equals to what we want, which is equals to that from 0. We said 2 millimeters is represented by r1. Okay, then you put everything, which is essentially rho dv. Check the hint that you're given in the question. It says the charge enclosed is equals to rho dv. So, but our rho is alpha, our rho is alpha r squared. Our dv is 2 pi r l dr. So if we are starting from the hint there, in place of alpha, in place of rho, we have put alpha rho squared, which is what we're given in the question, right? Then in place of dv, we have just put this expression, which is 2 pi r l dr. Length times width times height, so that we can get the charge enclosed. And once we get the charge enclosed, what do we do with the charge enclosed? Once we get the charge enclosed, we now come to this expression. Which you guys already know, that EA is equals to charge enclosed over epsilon naught. And our EA, in place of A, it's 2 pi r L. So our charge enclosed is equals to everything else are constants. Alpha 2 pi L. All these are constants. You remain with integrating what? R cubed dr. If you integrate r cubed, you will get r to the 4 over 4. Okay? And with limits 0 to r1. We said r1, that's where our Gaussian surface is. So it's equals to 2 millimeters. So r1 is equals to 2 millimeters. Okay? So which means our charge enclosed is equals to alpha 2 pi L r to the 4 over 4. We now have our charge enclosed. Now we come back to our expression, which we know that E 2 pi r1 L is equals to charge enclosed over epsilon naught. So we're now taking this charge enclosed and we put it in place of Q there. So E is equals to 2 pi r1 L is equals to alpha 2 pi L r1 to the 4 over 4 divided by this epsilon naught, which becomes epsilon naught like that. All right, but we're looking for E. So what did I do? We're looking for E, so E becomes equals to, if you simplify that, this is now a mathematical algebra, which is equal to alpha r cubed over 4 epsilon naught. If you simplify that, then you punch. I'm not sure if it makes a difference now. I'm not sure if it's making a difference now. I see there's a hand from Avile. You can unmute and share with us your contribution.
Hi, sir.
Hello, Avile. Thank you. You can go ahead.
The main question that I have, because of this problem, is the use of the integration technique.
Mm-hmm.
Are we using the integration technique in this problem because we have a non-uniform charge distribution, or there's another explanation behind that? It's just
Yes.
that part that I want to understand.
Yes, it's non-uniform, so we have to sum it up from 0 up to 2 millimeters.
So is that always the case when we have a non-uniform charge distribution, or there's another explanation behind this use of technique?
No. That's the whole point. And besides, that is why you've been given that hint to say the charge enclosed, you have to sum from 0 to 2 millimeters. It is because that the charge density is not the same at every given point. So you have to sum it up. That's why we have been given that hint. So I'm not seeing any other comments, guys. Sepo, you asked for a quick run through of the question. I think I've tried to summarize. I'm not sure if this helps or if someone still needs much more clarity than this from what I've just highlighted. Let me know via the comment. All right, I see Sepo is responding that he is following. So if there are no other questions, then we proceed. So what I'll say is, as you can see, that this is a conceptual question. Just to practice, you can go through this question again, watch the video maybe on YouTube. If you were taking down notes, just take down the notes. Then afterwards, just practice it again and see if you really have assimilated the nature of the problem and how we are supposed to solve it. Then question 35, which is going to be the last question for today. Question 35. I want us to solve this one together, right? I've been taking the lead on the earlier questions, but now that you are following, I guess we can do this one together. You tell me what I should and how I should go about this one. So pay attention to the question. A solid non-conducting sphere of radius 12 centimeters has a charge of uniform density 30 nanocoulomb per cubic meter distributed throughout its volume. Determine the magnitude of the electric field 15 centimeters from the center of the sphere. So this is our sphere and has a radius of 12 centimeters. There's a radius of 12 centimeters and there's a uniform charge density. Q equals to 30 nanocoulomb per cubic meter. And remember, Q is equals to rho V. Right, so we are to choose a perfect Gaussian surface. So if I may ask a question, I have two questions. What's going to be the shape of our Gaussian surface? And the second question, is our Gaussian surface supposed to be within 12 centimeters, or it should be having a radius greater than 12 centimeters? Look at the question. I have two questions. The Gaussian surface, what shape of the Gaussian surface are we choosing? And number two, the radius of the Gaussian surface, should it be less than 12 or greater than 12? Okay, so I'm seeing the comments are coming in. It will be interesting if everyone or most of us would put our thoughts, because I want to see if we are benefiting and if we are learning. So one, someone suggesting that it should be a cylinder, the sphere and greater than 12, greater than 12. Okay, so I'll respond from those three responses. So we said we need a perfect Gaussian surface. So the Gaussian surface must resemble the surface of the object that we are given. Yes, Tseko has corrected himself. So it should be a sphere as well, right? So it should be a sphere. And it should be greater. Why? Because we're being asked to calculate the magnitude of electric field 15 centimeters from the axis. So it should be out like that. So I'm glad that people are following. So it should be out like that. And we know that EA is equals to Q enclosed over epsilon naught. And A, what is our area now? Now the shape is no longer a cylinder, but it's now a sphere. Do you realize that? It's now a sphere. So what is the area of a sphere? That's the question. What's the formula of a sphere? Area of a sphere is given by what? Area of a sphere. We need to substitute, guys.
I am squared.
That was fast. Did you say 4 pi r squared or just pi r squared?
4 pi r squared.
Or 4 pi r squared. Thank you. So this is 4 pi. And which radius are we using? Is the radius of the Gaussian surface, right? Which is r, and this is r. 4 pi r squared. And our Q enclosed is rho v over epsilon naught. So this becomes E dot 4 pi r squared equals to our rho. The volume, it's a sphere. The volume of our object there, it's a sphere. What is the volume of a sphere? What is the volume of our sphere?
4 over 3 pi r cube.
4 over 3 pi r cubed, right? And this is the radius, small r, radius for our sphere, which is 12 centimeters. So I think our problem is half solved. Do you realize that our problem is half solved? That goes. So E now become equals to rho, which is what's the value? 30 nanocoulomb, which is 30 times 10 to the negative 9 times 4 over 3 times 0.12 cubed all over 0.15 squared. Please punch that and let me know what you get. Punch that and let me know what you get. I'm going to also quickly punch and see what do we get. Let's see if we get the same answer. So this is 30 times 30 times 10 to the power of negative 9 times divided by 4. I missed epsilon naught there. For epsilon naught, for epsilon naught. Times 8.85 times 10 to the power of negative 12 times 0.15 squared. Wow, 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 wow. I think I made a mistake. I may have made a mistake somewhere there. Let me punch this again. Do this 30. Charge is negative 9. Times I see Aviel is getting something. Then what are others getting for that working? Negative 12 times right. So this is what I'm getting, guys. 86.7. 86.779 Newton per coulomb. So I'm not sure if the rest of the guys were also punching, but I see Avile got a similar answer. So checking our choice there. It's 87, right? So it has been rounded up. So basically what we've done on this part of the question, we just applied the Gaussian law. So the charging closed is equals to, the integral of E dot dA is equals to charge enclosed over epsilon naught. And we're to look at our question, we've been given a sphere with a radius of 12 centimeters, right? And we're being asked to calculate the electric field strength at 15 centimeters. Hence, our Gaussian surface should enclose everything within 15 centimeters. So if it encloses everything within 15 centimeters, then it has a radius greater than the radius of the sphere. And once we've done that, you are left with substituting. You know that this is EA, the area enclosed by your Gaussian surface. Take note of the R, which is 15 centimeters, the area enclosed by the Gaussian surface. And calculating the volume, you're now considering the volume of the sphere. And this is what you get on this side, volume of rho V over epsilon naught, and then the rest is punching. So let me know if you've got any questions from what we have solved there. So this is what I had for us today. I'm not sure if you've got any questions from what we've solved today. So basically these questions were on applications of Gauss law. So always make sure you pay attention when choosing your Gaussian surface. Take note of the charge that you've been given. Also take note of the radius of your cylinder. It will help you to know the radius of your Gaussian surface, whether it's supposed to be enclosed or greater than the radius of the cylinder of the sphere, right? Considering where you're supposed to calculate the electric field strength. So I think for today, that is it. Find the other recordings that have been done on the earlier questions on our YouTube channel. So otherwise, this is what I had for you guys today. Show a thumbs up as we sign out to show that you guys did benefit from today's tutorial. Thank you, Tsepo. Thank you for your contributions as well. Thank you, Avuile, and thank you for your contributions as well. Alright, that is it for today, guys. Thank you for joining in. I see there's a number of you guys who joined in today. Thank you for joining. Join in again for tomorrow's session and you're going to benefit. So from me and everyone else in the studio, it's a goodbye.